PhD. I get started fall 2023. Jim has been here for a little bit more than a year with a summer internship at MSA. He works on security and resiliency of space systems, and he's going to talk to us about research that he's been doing for the past year.
Thank you. Yes, so as Dr. Lakim said, we are here for my preliminary exam. This will be approximately a 45-minute presentation, at which point I will open to the floor for questions, and then we'll have a closed meeting where I receive questions from the exam committee. Move the images down. Thank you. As she said, I am originally from the University of Pittsburgh during my undergrad, and I've been working here as a grad student for the last year. My preliminary exam talk is called TAL, Trust via Asynchronous Updates for Satellite Network Resiliency, exploring trust algorithms as they apply to satellite networks. During this talk, we'll be starting with an introduction motivation for the overall problem, and we'll be discussing some prior work that has been done in this field. After that, I'll be identifying some common limitations that were identified across various works, and then proposing my own TAL trust algorithm to address those common limitations of the resulting algorithm and have some conclusions. The overall goal for this work is to identify abnormally behaving satellites in satellite constellation networks. This involves identifying abnormal behaviors, such as dropping packets or other malicious activity. The other major goal of this work is to reduce the computational complexity and communication overhead relative to algorithms that have already been proposed for this task. The major motivations for this work are that satellite networks have become very attractive targets for due to their importance to various political and commercial organizations. And additionally, satellites in orbit are vulnerable to various insider and outsider threats. As you can see here, we have a picture of the Moonlighter, the target of the 2023 Hackasat competition, which showed that an operational satellite was, despite having modern security techniques, was still vulnerable to various attack methods. The major challenges of the work are that network observation of low orbit satellite constellations is very difficult due to their limited access to ground stations and remote nature. And additionally, some satellite attacks can cause significant damage to the network while still being very difficult to detect. We'll now be discussing some various attacks that we have seen for the satellite, how the satellite attacks can be. We will now be discussing satellites, and satellite networks are prime targets of cyber attacks. So satellite networks are very useful for many things, including navigation, observation, and communication. We saw satellite usage extensively in the recent Ukraine war on both sides, from the United States perspective and the Russian perspective. Additionally, hackers intercept data or cause strategic disruption, such as you can be seen on the right. This can cause severe damage to those using the satellites for those intended purposes. And reiterating from the previous slide, satellites are vulnerable despite using some standard defensive techniques. So we need some way to responsively identify when attacks are occurring. One potential solution to this is a trust algorithm. Trust algorithms are useful for detecting attacks, and they've been used in various domains in the past, such as vehicular ad hoc networks, IoT networks, and even more common things such as product recommendations on sites like Amazon or eBay. These things attempt to identify when malicious behavior is occurring and use this to identify an attack is occurring. Now, we can apply these types of algorithms to a satellite network, but there are some distinct differences between satellite network and these other domains. Specifically, that satellites do not allow for eavesdropping, this is because satellites have point-to-point communication laser transceivers. This makes it extremely difficult to determine if what communications are occurring if you are not directly part of the communication. Additionally, satellite orbits and connections are periodic and predictable, unlike ad hoc networks, where the connections are changing randomly and are difficult to predict. We have a very clear image of what the connections will look like very far into the future. Now, for trust algorithms, there are two main categories that we could potentially explore: centralized and decentralized algorithms. Centralized algorithms are when all of the relevant data is collected into a single computational unit. We perform the calculations, and then the results are distributed out to the various nodes for usage in usage and making decisions. This is similar to like a product recommendation where you see the aggregated score of this is the number of likes and dislikes and such. We can see decentralized algorithms are the contrary to that, where instead of aggregating all the information, each node has an image of a small portion of the information in the network, and we perform all the relevant computation at the individual nodes. This is similar to a vehicular ad hoc network where we have an onboard computer and it's using information from the other vehicles it's passing. Now, for satellite networks in particular, we're interested in decentralized trust networks. This is because satellites do not have a central computation unit that is easily accessible. The first thing that comes to mind is a ground station, but for low Earth orbit satellites, which are quickly rolling the Earth, access to these types of systems is inconsistent at best. Additionally, the individual satellites have enough computation power that they can perform these operations without significant resource usage. Now, decentralized algorithms work by combining two different types of trust into an overall trust evaluation: direct trust and indirect trust. Direct trust is directly measuring the behavior of an adjacent node. For example, determining, did the satellite drop my packet that I sent it? This would be a direct trust because I'm directly evaluating the behavior of another satellite or node. For indirect trust, this is relying your information based on recommendations. For example, if satellite 2 doesn't trust satellite 3 for various information, it could tell this to satellite 1, and then satellite 1 could use this information. For a brief diagram here, from the perspective of the green node, satellite M, it can perform direct trust on the 3 blue satellites around it that it's directly connected to. Meanwhile, it needs to rely on indirect trust for the 5 yellow satellites that it is not directly connected to. Now we've discussed satellite networks and trust algorithms. I will be discussing several trust algorithms that have been proposed in previous work that can be used for comparison. In this work, we're going to be discussing 4 decentralized trust algorithms that have been used for various applications in IoT and VNet networks. All of these algorithms rely on communications between nodes as their primary method of determining trust. And while these satellites were designed for different applications, they can still be applied to satellite networks. The differences between these satellites are they have varying storage and communication trade-offs, which can affect their performance. The first model we'll be discussing is the A model, which was originally created for IoT networks. This model counts the number of successful and unsuccessful interactions that it has with other nodes it connects to. The major strength of this model is that it's very lightweight. It's very easy to implement. You can see the visual representation. We have the scales of justice, where it counts the number of successful and failed attacks. A weighted average, it determines whether it trusts a node or not. The major issue with this algorithm is that it can only analyze one hop adjacent neighbors. So back to the image from before, the green node has a lot of very quick intuition about the 3 adjacent blue nodes, but has absolutely no way of evaluating the yellow indirect nodes in its current version. The second model we'll be discussing is the G model. This model was originally proposed for VNet networks. This model uses 3 custom metrics, which they call honesty, integrity, and reliability. It then combines these 3 values into a direct trust value using the concepts from fuzzy logic research field. This direct trust value is, during this time, it receives several indirect trust updates from other nodes in the network, and these are combined into a Q table, which is a concept from reinforcement learning. As an example here, you can see it has a relative trust for each satellite about each other satellite. In this example, you can see here satellite 2 trusts satellite 1 with a value of 0.01, and then on the contrary, satellite 1 trusts satellite 2 a different amount, a whole 1.0. The major strength of this particular algorithm is because it is based on reinforcement learning, it is extremely adaptable to changing environments, regardless of how it may evolve over time. The major weakness of this algorithm, however, is the three initial metrics that it uses to construct the direct trust value. The underlying assumption to make those three metrics is that it assumes that all nodes in the network should contribute equally to the system. This makes a lot of sense in like a sensor network where things are regularly producing a lot of information, but not as much sense when we convert to a communication network. The third model we'll be discussing is the L model. This model is designed based on Dempster-Shafer theory, which is a mathematical framework for dealing with uncertainty. This algorithm combined indirect trust values in a recommendation matrix, similar to the Q table we were discussing previously with some slight alterations to how it collects the data. These values are combined to create an overall trust value for a particular satellite using what's known as the Dempster-Shafer synthesis function. This is a function based on Bayesian probability theory that attempts to account for the fact that different indirect trust values can have different opinions. Satellite 2 really trusts satellite 3, but satellite 1 really doesn't. How do we deal with that discrepancy? The major strength of this feature is the Bayesian logic and probability features of the synthesis function. It's very good at resolving these types of discrepancies. However, the major weakness of this algorithm is its very large computational complexity. This algorithm is very computationally expensive and does not scale well to larger satellite networks. The final model from prior work that we'll be discussing is referred to as the M model. This model was created originally for VanNet networks, and it does something very different from the other models, where it actually breaks trust into two different metrics. An entity trust metric, where it's evaluating how much do I trust this particular node that is performing the action, and then secondary, how much do I trust the particular message that this node has received. By splitting the trust into these two different areas, it is able to account for a large number of different types of attacks that some of the other models don't do as well at. However, the weakness of this model is that because it is separating these two metrics, they are both relying on different subsets of the data it could theoretically be doing, and actually both our trust metrics end up performing slightly worse than if they had ended up sharing the information that they were working on. Now we've discussed several algorithms from prior literature. I'll be addressing some common limitations that have been identified in these algorithms and other algorithms from our literature review. The first major issue that was identified is that node assessment can be circumvented. A lot of algorithms talked about performing direct trust without having some sort of framework for actually doing so. You can see here that nodes need a reliable way to directly measure other nodes in the network. So if we have here in this example, same satellite network as before, the M satellite wants to send a message to I6 over on the right. To do that, the most easy way is to send the message to D2, and then it will arrive at I6. However, this gives D2 an opportunity to perform a malicious attack. It can refer to M that it did successfully transmit the message. Meanwhile, it actually drops the message. Because I6 is not expecting the message to come, this is an unanticipated message, there's no way for I6 to expect the message. There's no way for M to verify that it arrived, and the attack occurs without being detected. A lot of algorithms don't have some mechanism to account for this issue. The second major issue that we identified is an over-reliance on prior behavior. So prior work often assumes, if not explicitly, that a time of the attack is known, or that a malicious satellite or a satellite under attack is occurring specifically at the beginning of the simulation. Many algorithms don't account for the possibility of an attack occurring far down the line. You can see here in this example on the left, we have an attack occurring at the very beginning of the simulation. The satellite that is performing well has no issues, trust goes up, and goes into the trusted region, everything's fine. This is distinctly different from the satellites with lower trust that are performing the malicious behavior and remain in the untrusted region. The undesired outcome, which these models don't account for, is if the satellite has gained a large amount of trust by performing standardly over time, and then the cyber attack occurs where the satellite no longer is performing as expected. The trust begins to drop, but the satellite is still in the trusted region and likely will be for an extended period of time, where it can continue to cause further damage to the network. The final issue that we'll be addressing is the scalability. Many of these algorithms are computationally expensive and have a large amount of network overhead. Therefore, if we attempt to apply them to larger satellite networks, as we're seeing as a general trend for low Earth orbit satellite networks, that becomes difficult. We can see, for example, Starlink currently has over 5,000 satellites in orbit, with plans to expand that to over 12,000. OneWeb currently has 648 satellites in orbit, which is reduced from their original plan of over 1,900. And then finally, Amazon currently is in development for a 3,000 satellite network. When we grow our algorithms, a lot of these algorithms are designed with toy examples of satellites in the tens. When we expand these to thousands of satellites, we get a lot more latency and resource requirements than initially. As you can see here, we have some requirements in the order of cubic or quadratic orders, which requires a lot of resource usage. Now I'm going to discuss some common limitations. I'll be discussing my proposed Tau trust algorithm, which attempts to address each of these limitations. The Tau algorithm works by creating a finite state machine and sorting satellites into one of three states based on their behavior, which are the trusted, questionable, and untrusted states. Instead of updating this periodically, as most satellites are continuously or periodically updating, we instead use an asynchronous event-based method, where events are triggered by behaviors, and this contributes to what we call event counters. So we have two event counters, the negative event counter and the positive event counter. Whenever a counter is on a particular threshold, as indicated by these omegas on the figure on the right, the satellite will transition from one state to another. This can additionally cause additional events, which we'll discuss further. To avoid the common limitation of over-reliance on past behavior, counters are reset to 0 anytime we have a state transition. To just give a little bit more, an example on this, we have a satellite A is evaluating satellite B. Currently, it starts in the trusted state, where we have both event counters at 0. Over time, it's accumulating negative results, and the satellite transitions into the questionable state. At this point, both the counters are reset, and we continue evaluating again. As we receive both negative and positive events, the positive event reaches the transition threshold first. So the satellite transitions back into the trusted state. However, in this case, it again receives a lot of negative behaviors, and the event counter increases very quickly, so we drop into the questionable state again. In this particular case, the satellite performs a lot worse, and there are a lot more negative behaviors than positive behaviors. In this final state, the satellite transitions into the untrusted state, and which it will remain. To give a little bit more clarity here, satellites have a finite state machine, one for each other satellite in the network. So we have a toy example here. The blue satellite has 3 different finite state machines, one for each other satellite in the network. It currently believes that the red satellite is trusted, the black satellite is in a questionable state where it's showing some negative behaviors but not sure yet, and then the purple satellite has performed sufficient negative behaviors that it is no longer trusted. Now, re-emphasizing the fact that this is a decentralized trust algorithm, satellites don't necessarily need to agree on whether a satellite is trusted or not. You can see here in this similar toy example, the red satellite and the black satellite agree that in the questionable state, we have the purple satellite. It's performing a little bit suspiciously, but we're not certain yet. On the contrary, they disagree on the blue satellite. On the right, you can see the black satellite has placed the blue satellite into the trusted region. It for whatever reason, is receiving information that the blue satellite is performing as expected. Meanwhile, the red satellite has experienced more negative behaviors from it and therefore has dropped to the untrusted state. Now, I want to talk a little bit more about these events. Well, where are these events coming from, and how do we get them? So for direct trust, events are spawned by direct and indirect trust. We'll start with direct trust events. We're specifically looking for satellites that are dropping communications. And to do this, we have implemented an acknowledgement packet mechanism. A satellite sends a packet to its final destination, at which point the destination node generates an acknowledgement packet. This is sent back along the same path as the original message, alerting each node along the path that a positive event has occurred, because this means that all the satellites in the path successfully forwarded the packet. Meanwhile, if we receive a timeout, in which case no acknowledgement packet was received, this is likely an indicator that somewhere along the path, the packet was dropped, indicating negative behavior. So we can see here in this example, the source node sends a message to the destination. The message is sent and accesses all the packets. And then the destination generates this acknowledgement packet. It goes back along the path, and all three of those nodes can treat this as a positive event. This can help show positive behavior for other satellites in the network. For our indirect trust events caused by indirect assessment, we can use these state transitions. Whenever a satellite changes from the trusted state to the questionable state, or questionable to the trusted, et cetera, this is showing that a satellite is trusting positively the satellite, or it is negatively trusting the satellite. This can create a negative event for other satellites in the network. So when a satellite detects this transition from sufficient negative events, it generates an indirect trust report, which is sent to all other satellites in the network. However, to avoid flooding the network, we only generate indirect trust events about neighboring nodes. This is twofold purpose. It's intuitive that satellites that are communicating more often with their neighbors should have a better intuition of how that node is performing compared to nodes that are all the way on the opposite side of the network that have less interaction with it. Additionally, if every single satellite generated an indirect trust event when its satellite transitioned, this would result in a massive flooding of the network anytime one satellite transitions. If just D2 transitions into the negative, this would result in orders of magnitude more than is necessary compared to just the direct neighbors presenting these indirect trust events. Another benefit of this is that we can limit the damage of a bad-mouthing attack, when satellites will intentionally report negative behavior of other satellites, even if that negative behavior isn't actually occurring. Because we limit it to only direct neighbors, we can limit the effectiveness of this attack type. Now, this algorithm specifically has features for addressing each of the common limitations discussed in the previous section. A combination of our crypto and acknowledgement, a simple crypto system could make this acknowledgement packet, could guarantee that acknowledgement packets are only generated by a final destination. This allows for a direct way to evaluate direct trust of the other nodes in the network. Additionally, we don't have an over-reliance on past behaviors. The use of our finite state machine and the fact that the event counters are reset during every transition means there are no uncontrolled counters to create this bloated sense of trust that would take a long time to respond to. By automatically starting at the highest level of trust, our system continues to be responsive long after initialization. And then finally, this algorithm is very scalable. The storage requirements scale similarly to several of the other algorithms. However, the computational overhead is significantly less, and the communication overhead, less information has to be sent, especially since we are only updating asynchronously whenever an event occurs, compared to many of the other algorithms, which are sending an indirect trust report very periodically. Large amounts of data are being moved around. Now that I've described the functionality of the proposed trust algorithm, we'll be looking at some results. Now, looking at our second goal, the computational and communication overhead. As I mentioned, the tau algorithm uses far less communication overhead than all models, except for the A model, which doesn't use any communication, but that was more of a limitation rather than a feature of that algorithm. Here we have a chart showing the various complexities of the different steps. As you can see, the storage roughly scales quadratically, similar to several of the other algorithms. However, our communication is only quadratic compared to all the other algorithms using cubic communication overhead. Additionally, this communication update is occurring asynchronously compared to the periodic updates of other algorithms. And additionally, because the update version of our indirect and direct are functionally identical, simply incrementing the event counters, we can achieve an O1 computational complexity of the indirect algorithm compared to many of the other algorithms, which have to compute up to cubic levels of computational complexity, which scales a lot for some of these larger satellite networks. The second experiment, we wanted to see how does the tau algorithm respond to different types of attacks. So we're going to be looking at two types of attacks for our simulations. The first is a kinetic attack. This is when a satellite becomes totally inoperable due to various reasons, critical battery loss or physical damage to the satellite. Both of these can cause the satellite to become unresponsive and just simply refuse to forward communication. Detecting this type of attack is similar to a liveness test, where we're determining is the satellite still functioning. The second type of attack we'll be using is a black hole attack. This is a more nuanced attack where satellites drop a percentage of possible messages that it receives. This allows the satellite the malicious satellite to remain hidden and continue to create more damage to the network over a longer period of time. For this particular work, we'll be using a 60% drop rate, where 60% of messages arbitrarily are dropped, and the remaining 40% are forwarded on as intended. For this work, the tau algorithm performance is we use a custom simulator to compare these various algorithms in their responsiveness to these different types of attacks. We constructed a 100 satellite network in a torus topology, 10 satellites in 10 orbitals with 10 satellites in each orbital. These 10 satellites, we then randomly select 10 satellites to be malicious, indicated by the red dots here on the right. These satellites will perform one of the two attacks, either a kinetic attack, where they will simply refuse to relay communications, or they will do the black hole attack, where they will only forward a portion of the communications they receive. At each time interval, we then ask all the satellites in the network which satellites do they believe are acting maliciously. And to aggregate the results, we use three metrics: precision, recall, and F-score, which are taken from the field of data science. Precision roughly describes how accurate is a classifier. This is like looking for false positives, and how many results are we getting out of that, how much is actually what we're looking for. For our particular case, we're going to be looking at the number of correctly identified malicious satellites divided by the total number of satellites that were identified as malicious. For our recall, what percentage of the classifications were found? How many of the malicious satellites went undetected? In this particular case, we're looking at the number of correctly identified satellites divided by the total number of malicious satellites. In this work, that will always be 10. And finally, the F-score is the harmonic mean of the previous two values. This is just a clean way to combine the two metrics and give some intuition of the overall quality of the classifier. We can apply the classifier as a concept to trust algorithms by identifying trust algorithms as a malicious node classifier. In this case, all metrics are on scale of 0 to 1, with the highest value being ideal. So for our first simulation, we performed a kinetic attack at the initialization time of the network. This is similar to a lot of previous work. The tau algorithm performs reasonably well. You can see that the A and the G model very quickly have no loss in precision. The L model and the tau model have slightly lower precision. They're identifying slightly less, slightly more as malicious, even though they're not. And then the M model had about approximately a 0.4, where there were a lot more false positives. For our recall, which is our ability to identify the malicious satellites, all four of the 5 algorithms were able to identify malicious satellites all the time. The exception being the G model was not able to identify the kinetic attacks at initialization. Overall, this results in some trust scores. The G model was not very great at this particular experiment, and the M model did reasonably well, about a 0.5. The other 3 models performed reasonably well with very high identification, very high F scores. For our second experiment, there was slightly worse performance. We performed a black hole attack also at the time of initialization. The tau and the M model were the only models that were able to identify in the recall all of the malicious satellites. The G model had some success, but as you can see, due to the way it functions, it actually started dropping its malicious classifications. Meanwhile, the A model and the L model were not able to identify the black hole attack. The A model, for our precision, the A model and the L model did not identify any satellites as malicious, which is why they had a perfect precision. Therefore, the L and the M, the tau and the M models had the highest precision experiment, performing reasonably well about at a 0.8. And then the G model, with the reinforcement learning aspect, a bit of confusing performance. But overall, the M and the tau models performed the best during this particular experiment.
You misspoke for a second. You were talking about the F score.
Yes, yes. The final experiment that we're performing was a kinetic attack that occurs long after the simulation has begun, particularly 2,000 time intervals. In this model, the L, M, and A models were not able to identify any of the malicious satellites. They resulted in a 0 for recall and a 1.0 for precision. This is really hearkening to that over-reliance on prior behavior that we were discussing in the common limitations section. The tau model performed exceptionally well with precision relatively equal to the past 2 experiments, but also managing to identify all the satellites. The G model also had some success, but it took much longer for it to achieve the classification that we were looking for. Now that we've discussed the results of the tau algorithm, we'll conclude. Overall, the tau model addresses all the limitations we identified in the common limitations section. It has a mechanism for direct trust node assessment. It does not overly rely on past behavior. And then the communication overhead is very scalable relative to the other algorithms we addressed. This model was able to identify malicious behaviors in other satellites and has less network communication overhead relative to the other algorithms. I'd also like to draw your attention, the work discussed in this presentation has also been made into a paper, which was recently submitted to the Applied Cryptography and Network Security Conference, which will be held in June 2025. Looking to the future, we'd like to expand this algorithm further. There are other abnormal behaviors that we hope to leverage to create our trust metrics. For example, satellites in high radiation areas are likely to have technical errors, so we hope to use a radiation dosimeter readings to affect our trust. This will indicate malicious behaviors if it's in a radiation-heavy environment without directly indicating direct malicious intent. We also hope to test scalability to larger satellite networks. As we saw, some satellite networks are going to the order of thousands of magnitudes. Meanwhile, we only were testing with a 100 satellite network in this example. We hope to see how the algorithm performs for larger scale networks. And then finally, we intend to test more complex attack vectors, such as a bad mouthing attack, which I mentioned earlier in the presentation. I'd like to see how the tau algorithm is able to address these types of attacks. I'd like to take this time to thank my 3 committee members, Dr. Abdelhakim, Dr. Cunningham, and Dr. George, for their evaluation of this work. I'd also like to thank my industry supporters, Dr. John Ruffley and Dr. Sam Mergendahl, for their continued support during this research. And then finally, I'd like to thank everyone who attended this work today and anyone who couldn't be here to support me. I could not have done this work alone, so I thank you for all of your support. These are several references that were discussed during the presentation. And I now open the floor to questions. Yes.
How do you determine your thresholds for tau? I may have gone over it, I may have just blanked out.
No, so I go into this a little bit more in the paper. I used it's a method where I determined the indirect trust report has to be able to be the sole determinant for satellites that are very far away from where the evaluation is actually occurring. Therefore, we determined that the number of neighbors minus 1 times the event weight is the threshold, because then if, for example, there are 4 adjacent satellites, if one of them is not operating correctly and can't give reports, the 3 other satellites can give indirect reports. If an indirect negative event has a weight of 2, then we have a threshold of 6, because each of the 3 events indicates an event weight of 2, allowing all the satellites in the network to determine which are untrusted and trusted.
Can you clarify what's a weight?
Yeah. A weight is, sorry, each of the event counter does not count the straight number of events. We gave different weight values to different events, indicating that some events are more indicative of negative behavior than others.
Okay.
Joey.
In your simulation, were the questionable, were the satellites in the question state counted as malicious or trusted?
They were counted as trusted. We were looking specifically for how many were identified as untrusted or malicious.
Then I just have a more basic question. What tool did you use to simulate or model your network?
Python simulator. Python. Everything was coded from scratch. Yes.
Okay, because there's like some other tools like Mininet and then.
Sure. I was more concerned with the behavior of the algorithms rather than the performance of the network.
Okay, gotcha.
Like the latency of how quickly does this message get to there is not as important, rather than analyzing the specific behaviors.
Cool.
Here.
Was there a specific reason you made the simulation on a torus opposed to another interconnect kind of thing?
So torus topology is actually we're using I assumed a Walker Delta constellation, which is relatively the standard constellation metric for a lot of the constellation nowadays. And the Walker Delta constellation is layered on top of a torus topology, is the general idea for it. So that Starlink and Polar both use this type of topology.
Can you elaborate on how you are using or plan to use a cryptography to make sure that the message becomes?
So the general idea was that a simple public key cryptography scheme could guarantee that acknowledgement messages cannot be created by intermittent nodes. We saw this as a potential possible attack vector, so we just wanted to establish this crypto method as a defense. Since all these satellites already have existing standard protocols, we assume that that should be a reliable way to prevent that.
All right. Is there any worry about it, if you have a really long path, then you have to check so many different?
The assumption is that the public key is only attaches the final satellite.
Oh, I
the
see.
one that is generating the acknowledgement packet.
Okay, I thought it was in between as well. Okay.
Yeah.
So looking forward, especially to the bigger simulations, there's a lot of parameters at play. Is there an existing scenario that you can look to get realistic parameters, a black hole attack of 30% drop rate is normal or something like that? Or is it all just you gotta put it together yourself?
So the satellite constellation domain is relatively new. There isn't a large amount of attacks we can rely upon. We can look to some sort of attacks that have been used in other domains and attempt to use transferable knowledge, but it is still a relatively new field. Are there any questions on Zoom?
More questions? General line? Thank you so much.
I would also ask everyone that is on Zoom to leave, that has attended. Thank you. Thank you for coming to support me.
You can probably close meeting on.
Oh, okay.
Right, committee's all
Sure.
here, and I don't think you're supposed to record the questions.
Okay.
Yeah.